Sorry, I'm recording now. The determinant, right. So, okay, so start recording. So, so we're talking about an example of a set with a binary operation that does not have an inverse. And so the particular set we're talking about is the set of singular matrices with operation being multiplication. Right, so how can you determine if if a matrix is singular? By looking at the determinant, right? So A is singular. Of course, this is n by n, right? Singular does not make sense if it's not n by n. A is singular if the determinant of A is equal to 0. So now can you answer it? If two matrices are singular, is their product singular? Yes, right? And why is that? The determinant of a product is equal to the product of the determinants. But both of these things are 0. So the determinant of the product is 0. Okay, good. So that satisfies the operation is okay. Okay, so what's the next thing? Does this set have an identity? Does there exist an identity? That's the other kind of, that could be a special element. So by identity, I mean under the operation. Is that true? Within the set of singular matrices, is there an element where, or is there a matrix, if you multiply it, it does not change? So what I mean by that is, what does identity mean? Is there a matrix B where if you multiply it by A, you get A back? If you multiply it by A, you get A back. Does there exist a matrix like that? So if you say yes, what do you think it would be? I, the identity. Is I the identity singular? So I do agree that I is a matrix, that when you multiply it by a matrix, it doesn't change, or it doesn't change the matrix. But the question is, does the set have an identity element? So if you claim I is this matrix, that would need to mean that I is singular. And why is that? So you claim maybe 1, 1, 0, 0, 0. Well, here's an example of when that's not true. You have 1, 1, 2, 2, that's singular. I do agree this is also singular. But this does not act as an identity because this product is 1, 1, 0, 0. So what's the problem here? I is non-singular. Can someone say why that's true? What does non-singular mean again? Right, so non-singular means it has an inverse, and yes, the determinant is itself. The determinant is 1 also, true, and that means it's not 0, right? So when we're talking about these things, oh no, yeah, it's fine. It's yeah, it is its own inverse, that's fine. So yeah, so when we're talking about these things about identity element and inverse, we're saying do those exist within the set that we're talking about to begin with, right? Because yes, true, I is a matrix that doesn't change matrices. However, when I'm thinking about the set of singular matrices, I is not in that set. So that means the set itself, i.e. singular matrices, does not have an inverse. Does not have an identity, and therefore do not have inverses, which we also know true for singular matrices. Okay, so we're going to do more examples like this when thinking about when sets have inverses, when sets have identity. So it's kind of what we're going to focus on today a lot. So yeah, so let's, what we're going to do today is, well, we're going to look at special sets that that you can define binary operators on, and you can kind of group them into different classes of things. So like, if they behave this way, it might be this thing called a group. If other things behave different ways, you might call them different things. So there are a lot of different sets that you can define binary operators on. And all this will build up to the definition of a vector space, which is also a set with a binary operator with some other thing that we'll talk about called scalar multiplication. So that's going to be the goal for today, is kind of to build up our definition to a vector space. So meaning it's just some sort of special set with some special operator on it. Okay, so easiest of all these things is something called a group. So let's just say that these are special sets with binary operators. All right, so the first of these, oh, by the way, I'm not going to focus too much like with testing and homework on these first two groups and rings, not really at all, but they're good examples and for practice when thinking about testing of things, testing some properties about operators. So don't get too bogged down by the definition of these things. But we'll just see how certain sets satisfy these properties. Okay, the first type of special set is something called a group. So a group is a set with a binary operator such as the following hold. So this is something that is special to the binary operator, such that, well, first, which is true for whenever we're talking about binary operators, is that it's closed under the operation. Can someone remind me what closed means? So when I say a binary operation is closed in the set, what does that mean?
Do you mean like they're included?
Yeah, so what's included? So like if I take the binary operation on X and Y, exactly, yeah, the element doesn't leave the set, right? Like when I do this operation on X and Y, this thing must exist in the set. Like it doesn't escape the set. So really, this is kind of like maybe a zero case. Whenever we say binary operation, we kind of assume it's closed. For homework and stuff, you might be asked to check if that's true, but usually when you say it has a binary operation, you assume it's closed. Okay, so the next condition is about the operation, is that the operation is associative. Can someone remind me what associative means? So let's pretend like the operation, good, yeah. So good, got two different examples there. But there should be a plus in front of that first A, right? Juliana? Right, good. Yeah, so for example, for the plus operation, associative means you can group things however you want. So that's example for plus. For matrix multiplication, you can group the first two and then do the last, or you can group the last two and then apply the first. So if you want to, we did the function notation, which you don't have to do. But sometimes it's helpful to remember the function notation. Okay, so the second thing that it requires is that it has an identity. So we talked about that, right? And the third thing it requires is that every element has inverse. That's pretty broad, right? Associative is a pretty, nice operation or nice property of an operation you can have. Having identity and inverses are also things that you kind of would like to have. So this is pretty general. So, so let's just think about some examples and non-examples, just to get practice with kind of testing out these conditions. Okay, let's say we have integers with with normal addition. So let's check case 0. Is it closed under the operation? Is the set called integers closed under addition? So what does that mean? If I take two integers and add them, do I get an integer back? Yes. Yes, it is closed, right? If I take an integer n plus an integer m, I get an integer back. Okay, is it associative? Well, yes, because our first example was addition. That was above. Does it have an identity? Is there an integer where if you add it to another integer that it doesn't change? Yes, and it's 0. So n plus 0 is equal to n. 0 plus n is equal to n. Good. And 3, are there inverses? So remember, inverses with respect to the operation. Do there exist additive inverses within integers? So given n, is there a number that you can add to n and you get 0? Correct, the negative of the number, right? Negatives are integers, right? So yes. So because it satisfies all, since it satisfies all these complements, or all these axioms, that means this thing is a group. Number 1, it's associative, the operation. The number 0 is closed, which means that taking the sum will always give you an integer back. Okay, so questions on kind of seeing how, how you can check these operations? Okay, so let's do another one. I'll write out the requirements again. So it has to be closed, associative, has to have identity, and has to inverse. Okay, so let's check the same set, but let's use a different operation. Let's take integers. So from now on, I might say integers just as kind of Z with a line through it. I think I talked about that last time. And let's let the operation be multiplication. That is a binary operation, right? All right, so let's check. Is that closed? Is that operation closed in the set? So meaning, if I take two integers and I multiply them together, do I get an integer back? Yes. N times m is an integer. Yes, associative, right? N times m, I don't know, let's say p. You can group however you like. Yes, identity. What is the identity in multiplication? 1. N times 1 is equal to n, and 1 times n is equal to n. Now do inverses exist? So remember what we say in the beginning of class. When we say inverses, we mean it needs to be in the set. Okay, so 1 over n, yes, is maybe reciprocal of n, and that equals the additive or the multiplicative identity. But what is that? Oh, if we multiply by 0, yeah, that's fine. A number times 0 is still an integer, so that's okay. And also for identity too, right? 0 times 1 is 0, so that's okay. So the claim is, so we do think of, yeah, the reciprocal of a number does multiply to be 1. However, is the reciprocal of an integer inside the set of integers? No, yeah. So that's the big thing about, inverses and identity, right? These special elements need to lie in the set. So, for example, 2. 2 times 1 over 2 is equal to 1, but 1 over 2 is not an integer. Another way you can say that is, exactly, integer is like a whole number, and it can be negative, can be positive, and 0. But fractions are not integers because they're not whole. Right. So yeah, I probably should say that. So integers are whole, positive, negative, and 0. Another way you can think of it, they're fractions with 1 in the denominator. Or we can say simplified fractions. So 1/2 can't be simplified further to a 1 in the denominator. So it's not an integer. All right, does that make sense? So the biggest thing to take away is, how can you say that last statement that it does not have an inverse? Because I mean, yes, it kind of has inverse in the bigger set, which is just numbers, but it doesn't have a set in the doesn't have an inverse in the set that I care about called integers. Okay, let's do a couple more. So remind yourselves, closed, associative, identity, and inverse. Let's do m by n matrices. This is for a specific m and n. And let the addition, let the operation be a matrix addition. Okay. What do we think? Is it closed? If I add two matrices together, do I get a matrix of the same dimension? Yeah. Is matrix addition associative? Yes. Is there an additive identity? The zero matrix, but Aij is equal to 0 for all ij. Yes. And is there an inverse? And yes, what is the inverse? So if I have A plus B is equal to 0, what do we call B? Inverse of A. So yeah, how do you describe entries of the additive inverse of A? Yeah, all entries are negated. All right. Let's do another one. How about non-singular? N by n matrices with addition. What do we think about that one? Is it closed? If I take two non-singular matrices and I add them together, do I get a non-singular matrix back? Yes, you sure about that? If this is non-singular and this is non-singular, is it true that this is non-singular? So remember, it's addition, not multiplication. Not always. Yeah. Can you think of an example where it's not? Like, can you find two non-singular matrices whose sum is a singular matrix? There's always one like perfect example for this. What's the most boring singular matrix you can think of? Let's see. 1 0 0 1 plus 0 1. 0 1 0 1 is not, but this makes it singular. That is singular. And these are non-singular. Yeah, I like that one better, Samantha. Just take a matrix and its inverse. 0, I think, is the most boring matrix, right? That's singular, right? Obviously, this is singular, right? 0 times anything is 0. And both of these could be non-singular. So now, one thing about, when you prove these things, you'll prove them for vector spaces, but there's not much to prove for a group, for example. is that if you can find one case where one of the things fail, then immediately you don't have to do anything else, right? Because it fails this condition, that means it's not a group. So you don't need to check every single thing. All you need to check is that one fails. Okay, any questions on that? So do you see, the closed part of the operation is important to check. All right. Now let's do it the same thing, but with multiplication. Non-singular, but multiplication. And this is matrix multiplication. So we actually talked about this earlier, right? If A and B are non-singular, is AB non-singular? What do we think? So if you have two matrices that are non-singular, is their product non-singular? Yes. And why do you know that? I think you mean not zero, right? Determinant of both is not zero. Yeah. The determinant of AB is equal to the determinant of A times the determinant of B. And neither of these things are zero. Right? Non-zero means determinant's not zero. It has an inverse. So that's good. All right, so let's do the first criterion is it associative. And yeah, if we say matrix multiplication, it's associative. So usually the properties of the binary operator kind of are obvious sometimes if there's something that you know. Does there exist an identity element? Is there a matrix such that where if you multiply by A, you get A back? I, yes. And the question is I non-singular? Yes. Couple of reasons, right? I times I is equal to I. The determinant of I is equal to 1, which is not 0, etc. And 3, inverses. Do non-singular matrices have inverses? Yeah, that's really their definition, of course. All right, so this is good. This is a group. Okay, so you kind of get the idea of like, checking these properties. So I'll do one more that you might be familiar with. So rotation, the set of all rotation matrices. So the rotation matrix, right, was this thing you thought about in your midterm. So one thing I didn't ask on the midterm, and then with matrix multiplication. I didn't ask you to actually multiply two different rotation matrices, but can you guess what it is? Like if I take r theta times r different angle phi, do you think you know what the angle would be? Good, theta plus phi. I didn't ask you to do that one because the sum angle can be a little harder to work with. But yeah, so I think intuitively this is true, right? If you rotate by an angle, then you rotate by an angle again, right? It should be the sum. So that's cosine of theta plus phi, negative sine of theta plus phi, sine of theta plus phi, and cosine of theta plus phi. So if you do that out, and it turns out that it factors into each individual rotation. I won't go through the whole proof of that because I thought about it on the midterm, at least with squaring. Yes, it is associative because it's matrix multiplication. Inverse or identity, that's next, right? Is the identity matrix a rotation matrix? What angle theta? What angle theta makes identity? Zero, yeah. R0 is equal to I. And yeah, there not just zero makes I, but maybe on the test you found out that any multiple of 360 also gives you I. And inverse. Yeah, or you can say R 2 pi n, yeah. Inverse. So can someone say what the angle is for inverse? You figured it out? Minus theta, yeah. R of negative theta. So you hopefully figured out if you plug in negative theta, it was the same as just doing the inverse of this, which if you just did the normal 2/2 calculation, it was cosine and then sine, negative sine, and cosine. And how do you get from here to here? Right, we have symmetry of sine and cosine. So that's how the negative theta goes away. Because we have some, we know cosine of negative theta is cosine of theta, and sine of negative theta is negative sine of theta. Okay, yeah, so this is also a group. So just wanted to relate that. Okay, I want to do one other one. Let's do 2x2 non-singular. However, I want all entries are integers. This means I don't want any fractions in my matrix. I just want integers. Does that make sense? So, for example, this is not an element in the set. This is an element of the set. Okay, and then I want my operation to be matrix multiplication? Okay, so it's the first one. Is it closed under multiplication? So if I have two 2x2s, I'm not doing anything higher than that, 2x2 matrices that are non-singular. Well, first of all, if I multiply them, yes, I get non-singular, right? A, B is non-singular. So the second question is, are all entries of A, B integers? What do we think? Think about what matrix multiplication does and think about integers. So like, let's just kind of do an example. A, B, C, D. Yes, X, Y, Z, W. Let's pretend they're all integers. I'll just do the first entry, the product. AX plus BZ. This is an integer. Yeah, so, and. Yeah, so that's what I'm defining set elements to be, is that it's are all 2x2 non-singulars where all entries are integers. So like this thing is non-singular, but not all entries are integers. Yeah, it has to satisfy both things to be in this special set. Does that make sense, the definition of the set? So two things need to be satisfied, both, well, three things. 2x2 matrices, non-singular, and integer entries. Okay. Oh yeah, and so why is that true? Why must, so if all of these things are integers, why is the matrix product? Why will all things in the matrix product be an integer? So for example, this first entry here is AX plus BZ. Is this an integer? So A, B, C, D, and X, Y, Z, W, all of these are integers. Well, let's break. Yeah, integer addition is closed and multiplication is as well, right? If I multiply two integers, I get an integer back. So when I do matrix multiplication, all I'm doing is multiplying things and I'm adding things. So if I multiply two matrices that are full of integers, well, the product must be full of integers. Let's just do an example, right? Let's have 1, 2, 3, 4. Those are integers. And let's make random integers M, N, P, Q. So all of these are like whole numbers. So the product is N plus 2P, M plus 2Q, 3, N plus 4P, and 3M plus 4Q. Do you see why all of these things have to be integers? Yes. Right. Again, integer times integer is an integer. Good. An integer plus integer is an integer. Good. All right. So you don't need to overthink it. Associative, yes. Because this is matrix multiplication. Okay, now let's think about identity. Is the identity matrix inside this set? Is the 2x2 identity non-singular and whose entries are integers? Yes. right? Because 1, 0, 0, 1, all of these things, these are all integers. Okay, now, how about inverses? Let's say you have a 2 by 2 non-singular matrix where all entries are integers. Is its inverse? Think about its inverse now. Is it necessarily true that all those entries need to be integers? No, yeah. Can you think of an example? Not always, yeah. So first of all, what is the, let's just maybe start there. What is the definition of matrix inverse for 2 by 2? Do you remember? There's a formula we came up with, right? For 2 by 2, it's nice, right? It's 1 over determinant. And then, yeah, AD minus BC. And switch and negate, yeah. So you switch the diagonal elements and you negate these elements. Okay, so these are fine, right? These are integers. Right, integer, yeah, inverse integer entries may not be nice, because then, yes, then I have to multiply in this 1 over determinant, right? So dividing by determinant, dividing entries by the determinant, may not keep it an integer. May not keep entries as integers. Yeah, no fractions allowed here. We don't like fractions. Okay, so let me ask you this. Is there a condition? Is there a third thing I can add to this already long definition of the set so that inverses do have all entries as integers? So think about our formula for inverse. What do you think the determinant must be to ensure 1? Is there anything else? Any other determinant or negative one? Yeah. So 2 by 2, non-singular, entries integers. Just adding to the list. And, sorry, I'm a little laggy right now. And the determinant is 1 or negative 1. Then inverse exists. So I think this is the first time we talked about determinants where I actually cared about the number, not just that it wasn't 0. So when the determinant is 1 or negative 1, that's kind of nice, is that you are integer matrices, their inverses are still integer matrices. This is a pretty cool example of a group, but let's enough about groups. When we talk about vector spaces, groups will come back into play. But any questions on that? Did everyone see why that's true? Like, if I just add in that extra condition where the term is 1 or negative 1, then suddenly inverses exist in the set. So getting good practice with our operations. Okay, so I won't go too in depth with this next special set because the set that we really care about is right after. But the next like special set is called a ring. And what's interesting about these is actually it's a set with two operations. Two operations. Binary. So the first operation it needs to satisfy these things. It needs to be associative. It needs to be commutative. There needs to be an identity. And there need to be inverses. So this looks a lot like a group, but we have this extra thing that we want it to be commutative. And of course, I'm also including closed. Okay, so we'll usually call this plus. So the second operation, it needs to be associative. And it needs to be distributive. So can someone say what distributive means? So let's call this operation times. So if I have A and then the second operation and then B, this first operation C, yeah. It's A second operation C or B plus A, sorry, I'm just laggy today. A second operation C. So even though it looks scary, oh no, two binary operations is actually more familiar. It looks more familiar than what we're used to. However, some things will have to get even more specific. Yeah, of course, it needs to be closed. Closed. So I won't do too many examples, but I'll do two that are interesting. So remember, so if we have integers where the first operation is plus and the second operation is times, this actually forms a ring. So for plus, we talked about already, it's closed, it's associative, it is commutative, has inverses, 0 and then negative n are inverses. And for times, it is associative and it is distributive. So notice for rings, I don't require multiplicative inverses or identity. So that's what makes integers okay, because they don't require multiplicative identities. So all I have for multiplication is that it's just associative and distributive. And the other one I'll talk about is just n by n matrices. And you could probably check that. So with plus and matrix multiplication. And again, if you don't require multiplicative inverses, then all matrices are fine for that. But again, I'm not going to focus too much on this one because I want to talk about a special type of ring which has a bit more properties. But everyone get what I mean by two operations? So it's kind of, it sounds more like what we're used to, like things with You can add things together and you can multiply things together. Those are two different operations, but you can still talk about it. You can still talk about the same set with different operations. Okay, so I'm not going to focus too much on that one, but the big one is field. So field is a special type of ring. So it has all the properties of ring, but multiplication is also commutative, has identity, and has inverse. So once you add these three things, now this is actually a very nice type of set. So let's think about that. So can you think of a set that has all these things? So plus is commutative, associative, has identity, it has all the nice things. Identity, inverse. So I'm very laggy, so it's hard to write. Multiplication is commutative, associative, identity. Oh, sorry, I should say in here, except for additive, for additive identity. Inverses and distributive. There's a lot. Oh, turn off camera. That's probably a good idea. Let me do that. Thanks. So, what's the kind of so when you think of like a set, what's kind of the easiest one to think about in terms of sets with operations, like besides empty set? When you think of what's a set that you know that has two operations on it? Like before even walking in this class, integers. How about even like more than integers? Those are pretty specific, right? Real, yeah. So real numbers are, we just call them numbers, right? Real numbers are a field. So what was wrong with integers is because they don't have multiplicative inverses, right? But real numbers do, right? If you take a real number, what's its inverse? Multiplicative inverse. Reciprocal, yeah. So good. And all those other things apply, right? Now, can you think of any other set of numbers that work, that might work? So it's kind of one step up from integers, but a little down from reals. Yeah, rational numbers are also fields, is a field. We won't talk about rational numbers too much. If you're curious, the little symbol for rational numbers is for some reason a Q with a line through it. And yeah, this is also true because what's the reciprocal? I said it, but what's the inverse of a rational number? Yes, the reciprocal. And the big thing is that this is also a fraction, also a rational number. That's much better now. And one other thing you do have, which we won't talk about, but you might have a homework question that talks about it, is complex numbers. C. So those do have. So do you know what what I'm saying it? What the inverse of a complex number is? The reciprocal. And if you put this in A plus BI form, I'll let you figure it out if you don't remember. It's A over A minus B plus or minus B over A minus BI. Sorry, this is A squared plus B squared. This is the minus. So yeah. So if you remember from pre-calc, you should know how to do that. But so that also forms a field. The field that we're going to care about the most is real numbers. So real numbers are kind of like the quintessential field. So it's like really who cares about anything else, but real numbers are the thing we care about. So now I just think it's funny that the more kind of special conditions we put on a set, the kind of easier it gets, right? Real numbers are very easy to work with, or we work with them all the time, right? But they have so many conditions, right? There are so many properties. And the easiest one is like a group, but you can come up with some really weird types of groups because it doesn't require much for it to be a group. So I think groups are very cool. There's whole fields just talking about this thing called a group. It's kind of a weird thing about math. The more complicated and specific you get, somehow kind of easier it gets because there's less things to need to prove. Okay, so any questions on that? So we'll talk about fields. Okay, so actually let's go. So the last type of set there is that we'll talk about is a vector space. So finally got to the word vector. So a vector space is a special set with, it's a set with a binary operation lagging again, and there's a corresponding field. Corresponding field with something called scalar multiplication. So we'll define what that means, scalar multiplication. We've talked about scalar multiplication in the past. We kind of just treated it not really rigorously. We just said, and you do this. So we'll really say what scalar multiplication means when you're, when I mean scalar, I mean things in a field. So scalar is equal element of a field. So in this class, we'll only really be talking about the real numbers. So don't be too worried about what a field is. Just we can treat them as real numbers. So let's talk about what the binary operation has to look like. And this will look familiar. So let's think about the properties of the binary operation. So we'll usually call the binary operation plus, maybe with a circle around it, or just plus. Yeah, if it's maybe the one that we're more comfortable with. Okay, so what must be true about the binary operation? Well, obviously it must be closed. That's kind of just always given. It must be commutative. It must be associative. We need an identity. And we need inverses. This looks familiar, right? What do we call these things? Do you remember the name of it? A set that has at least 3 of these things. This is actually a group. It's a group whose addition or whose operation is also commutative. As well. So we went back to the group. Everyone see that? Like, so you have your set, and if you only think about the operation on the set, it actually turned out to be this thing called the group. But with the additional requirement that it needs to be commutative, which is still a group, which is a little extra flavor to it. Okay, so that's all in the binary operation. So if that's all we had, then we just call vector spaces groups. So why do we call it vector spaces? Is because we also consider how it interacts with a field. So let's explain what that means. We'll call the field F. Usually this will be R. Now, something important to note is that the field element is not part of your vector space, but it acts on it. It does something to vectors. So here's what we're going to call scalar multiplication. So scalar multiplication is a function f that inputs field element, which we're calling scalar. It inputs, I'll just say scalar, inputs scalar, and it inputs, I'll use the word vector, but I'll say set element. And it outputs a vector. So does that make sense? So let me give you an example of when we use that. So let's say 2 is the number, and then my vector is 1, 2. What does scalar multiplication do? We define scalar multiplication when we talk about vector, properties of matrices. What do we do to that? What's 2 times the vector 1, 2? Yeah, 2, 4. So do you see how this is a function that inputs a number? This is not a vector, or at least it's not a 2x1 vector. It inputs both a number and a vector, and it outputs a vector. Okay, everyone see that? So 2 is not a vector. So this is not multiplying vectors. You're taking a number and you're doing this thing called multiplication to the vector, and you output a vector back. We'll never output a scalar back. Okay, so what are properties of this function? So usually I'll say if the scalar is alpha, instead of using this function notation, I'll usually say alpha and then like a circle v, and then whatever it is, so maybe like alpha v. Okay, what are properties of the scalar multiplication? It needs to be, well, first of all, closed. It needs to be distributive in both field and set. So what do I mean by that? Is that if I take a sum of field elements and multiply it by a vector, then I can distribute the vector in. And it works both ways. If I have a field element plus a sum of vectors multiplied, then it's alpha plus alpha W. So everyone see that? So these are different pluses, right? This is field plus, and this is vector plus. This is also vector plus. Any questions on that? See, right? We're adding different things. On the one hand, we're adding field elements. On the one hand, we're adding vector elements. All right, 2. This is a pretty important one, and it needs to be compatible with field multiplication. So what I mean by that is that, let's say I have alpha times this will look like associativity. If I have alpha times beta times v, it's the same thing as multiplying the field elements on the side and then multiplying the vector by the element. So this kind of looks like associativity. But the reason why we don't call it associative because there's 2 different operations here. This is scalar multiplication. But this here is field multiplication. Everyone see the difference there? Alpha beta together is field multiplication, but alpha circle is scalar multiplication. So that's why we call it compatible. They're compatible with each other. Associative would mean like all the operations are the same operation. And the last thing we have is identity is preserved. So what do I mean by that? It's kind of something you should expect. Let's take 1. Sometimes I like to use 1 sub f, meaning the field identity. If I take 1 in the field and I multiply it by the vector, what do you expect? If this is supposed to be nice, what do you think it would need to be? Yeah, you would hope for it to just get v back. All right, so it's a lot to soak in. But I think the most interesting part about the vector space is all in the scalar multiplication, right? The first part is like, okay, this is a binary operation. We kind of talked about these. These were this forms some nice things group, but the scalar multiplication is where things get interesting. Oh, the sub f is just to indicate that this is in the field, as opposed to it's not 1, not the vector called 1, if we were to say that. So yeah, any questions just on the definitions? It's a lot to check when we check for vector spaces, but when we do examples, we'll see why all these definitions are nice and needed. So let's just do a very easy one. What do you think the easiest vector space is? Like, oh, and besides empty set. So what's a set that has a binary operation and it has this multiplication thing? So we talked about it earlier. Real numbers, yeah. So let's just kind of break down why real numbers are a vector space. So the set is real numbers, and we're going to use plus. Multiplication may not work. You might need to check it. The field is R itself, and scalar multiplication is what you think it is. Alpha times X is equal to alpha X. So just normal real number multiplication. So why does this work? So first thing you do is ignore scalar multiplication and only look at the set with addition. Are real numbers closed under addition? Yes. Is real number addition commutative and associative? Yes. Is there identity? Yes. Is there inverses? Yes. So you've already done half of it. Now, is scalar multiplication closed? If I take two real numbers and I multiply, do I get a real number back? Yeah, of course. Is it distributive? Yes. And it's compatible. Well, yeah, it is. This is associativity when talking about just normal multiplication and identity is preserved. So what I like to think about vector space is that it's kind of generalizing what we think about real numbers. So for example, another vector space out there is 2 by 1 vectors with vector addition and real scalar multiplication. So we are out of time now, but next time we'll go through some vector spaces and things that are not vector spaces and see why or why not it's true. I gave you homework, but I spent a lot on, probably start it. Yeah, so next time we'll do a lot more examples on vector spaces, and we'll actually look more on vectors on a plane. How do these things look with vectors on a plane? So things that you might think about when you think about vectors. We'll finally get arrows for vectors. Okay, so I'll see you Monday, and I believe we do have Wednesday class, right? We don't have off. It's Thursday, we have to start to have off. Midterms probably after Thanksgiving. I'll work on this weekend, but I don't think we'll get them all done this weekend, but definitely after. Hopefully after. All right, so you can head out. Stick around for questions if you have. No, the final will be shorter. I like to have a long midterm, really focus on it and understand what's important. And the final is going to be not as long. Right. Maybe. Oh, office hours, they're before class. So before 5, I start at 5 on Wednesdays, office hours. I'll just be on here until class. And then Mondays, the hour before class, so like 6 to 7. And on Zoom as well, so same length. It's this room. Sure. If you're confused about vector spaces, we'll do a lot more next time. Yeah, we have talked about scalar multiplication. Yeah, that was actually a nice thing about scalar multiplication on matrices and vectors. Was that you can express scalar multiplication just as matrix multiplication. because it does the same thing as just a bunch of type 2s. That's what scalar multiplication is. It's just doing a lot of type 2s. So why do we call it scalar multiplication here? Is because it has all these properties. Scalar multiplication times a matrix is a matrix. It is distributive. If you have alpha times A plus B. And now this is important, like, see what the difference between scalar multiplication is that this is not matrix multiplication, right? It's scalar multiplication. Compatibility, you can check that out. And identity, yeah. So we've talked about it, but we haven't generalized. This is generalizing what scalar multiplication is. So we'll talk about different ways. So this thing can be a lot of different things. I'll let you think about this one. This is one of my favorites. Let's say alpha times n is equal to the floor of alpha times n. So maybe that's my scalar multiplication. One of these things fails. Like for, let's say, integers. So let you think about that. I'll do that one next time. But obviously identity is preserved. The floor of 1 is 1. You might want to think about these. And it is closed because the floor is an integer, so integer times integer is integer. But one of those things fails, at least one. They both could fail, but I know at least one fails. Oh yeah, I need to stop recording.